There is something you have never questioned, something so fundamental, so woven into the fabric of your every waking moment, that to doubt it feels almost offensive to reason itself. You have never once woken up in the morning and wondered whether it was real. You have never stared at a clock and thought, maybe this is measuring something that doesn't actually exist. You have simply lived inside it, moved through it, been shaped and carried and ultimately worn down by it. The way water is shaped by a river, it has always believed it was flowing through. But here is what the evidence is starting to suggest, quietly, insistently, from laboratories and equations and the deepest corners of theoretical physics. Time, the very thing that feels most undeniably, inescapably real, may not be real at all. And once you start pulling on that thread, once you really start looking at what the science actually says, the entire structure of what you thought you understood about reality begins to tremble in a way that nothing in your ordinary experience could have prepared you for. Right now, at this exact moment, you feel something. You feel the present. You feel the specific, irreducible sensation of being here, of existing at this particular point in the sequence of events that you call your life. Behind you stretches a corridor of memory, a long trail of moments that have already happened, moments that exist now only as impressions, electrical residues fired across synaptic gaps in the dark architecture of your brain. And ahead of you, just slightly out of reach, stretches the future, the territory of anticipation and worry and hope, the domain of everything that hasn't happened yet. This three-part structure, past, present, future, is so ingrained in the way you experience reality that it might as well be the shape of existence itself. It feels like you are a traveler, moving in one direction, leaving behind a world that has already been visited and pressing forward into a world that is waiting to be explored. That feeling is so constant and so convincing that to question it feels, at first, almost like a joke, like questioning whether the ground is solid. But here is the strange part. That feeling, that vivid, undeniable, moment-to-moment sensation of moving through time, is something your brain constructs. It is not something that physics has been able to independently verify, and that distinction matters enormously. Think for a moment about how completely your sense of time structures everything you are. Your identity is a story you tell about a sequence of events. You are the person who grew up in a certain place, who made certain decisions, who became something over the years. The word years itself assumes time is a container that things can be measured inside. Your plans depend on a future that you assume will arrive. Your grief depends on a past that you assume has genuinely receded behind you. Your sense of progress, of becoming better, of working toward something, every single one of these experiences exists only because you believe in time. You believe that yesterday was real. You believe that tomorrow will come. You believe that now is a specific, privileged location in a sequence, a real place you are actually standing in. And this belief is not naive or foolish. It is reasonable. It matches everything you have ever experienced until you start looking at what the universe actually does at the level of its fundamental laws. Because when you do that, when you really follow the physics all the way down to its roots, something very unsettling starts to emerge. The universe, at its deepest level, does not seem to require time. And that is not a poetic observation. That is a scientific one. To understand why that claim carries any weight at all, you need to first sit with the version of time that most of us quietly assume to be true. Newtonian time, the kind that Isaac Newton formalized in the 17th century, and that most of us still operate on intuitively, is absolute. It is universal. It ticks at the same rate everywhere in the universe, like a great cosmic clock whose second hand sweeps impartially across all of existence, marking the same intervals for every object, every particle, every living creature, regardless of where they are or how fast they are moving. Under this model, if you and a friend both look at synchronized watches at the exact same moment before one of you boards a plane and flies halfway around the world, those watches will still read the same time when you are reunited, because time itself has passed equally for both of you. The universe has advanced uniformly by the same amount. 1 second here is 1 second there. This felt so obvious, so self-evidently correct, that Newton didn't really argue for it so much as he simply declared it, the way you would declare that water is wet. And for more than 2 centuries, nobody had a good reason to argue back. Everything in the observable world seemed to confirm it. Time appeared to be the one truly universal, unvarying constant, the great common denominator of all experience, the background hum that everything else was arranged on top of. Then Albert Einstein was born. Einstein did not set out to destroy time. He was trying to solve a much more specific and technical problem, the apparent inconsistency between two sets of laws in physics, the mechanics of moving objects and the equations governing light and electromagnetism. What he discovered in the process of working through this inconsistency was something so disturbing to common sense that even he seemed to spend years grappling with its full implications. Time is not absolute. Time is not universal. Time is not the same for everyone. Time, Einstein demonstrated with mathematical precision, is elastic. It stretches, it compresses, it bends. The rate at which time passes for you depends, in a measurable, verifiable, physically real way, on how fast you are moving and on the strength of the gravitational field you are moving through. This is not a theory or a guess. This is one of the most rigorously tested and experimentally confirmed results in the entire history of science. It is called time dilation, and its implications are so strange that the only reason most people don't walk around permanently destabilized by it is that they never encounter the conditions under which it becomes significant in daily life. Here is what time dilation actually means in practice. If you could get on a spacecraft and travel at a substantial fraction of the speed of light, let us say 90%, the speed of light being roughly 300 million meters per second, and you flew away from Earth for what felt to you like 1 year, when you returned, you would find that something like 2.5 years had passed on Earth. Your clocks would have ticked slower, your heartbeat would have been slower, your biological aging would have proceeded more slowly. You would not have experienced this as a distortion. You would have felt entirely normal. It would have felt like a year to you, because for you, it genuinely was a year. But for everyone else, more time had genuinely passed. This is not an optical illusion. It is not a matter of clocks malfunctioning or signals being delayed. Real, physical, biological time actually passes at different rates depending on relative velocity. The universe is not ticking uniformly in the background. There is no master clock. There is no universal now. The present moment you are experiencing is genuinely different from the present moment being experienced by someone moving at a different speed relative to you. Your now and their now are not the same now. They are displaced in time relative to each other, in a way that is fully real, fully measurable, and fully confirmed. And velocity is only one dimension of this strangeness. Gravity also bends time. The stronger the gravitational field you are inside, the slower time passes for you relative to someone in a weaker gravitational field. This means that right now, at this very moment, time is passing slightly faster at the top of a mountain than at sea level. It means that the clocks on GPS satellites which orbit the Earth at altitudes where gravity is weaker run slightly faster than clocks on the surface, and engineers have to correct for this difference constantly, or the entire GPS system would drift into uselessness. It means that the clocks at the base of the Empire State Building tick ever so slightly slower than the clocks at the observation deck at the top. These are not metaphors. These differences are real, and they are measured. The effect is small in those everyday examples, but near the event horizon of a black hole, the effect becomes extreme. Time, near a sufficiently massive object, slows to a crawl. An astronaut falling toward a black hole would, from the perspective of a distant observer, appear to almost freeze in time, their image becoming redder and dimmer as they approach the event horizon, but never quite crossing it, at least from the outside perspective. From the astronaut's own perspective, they would cross the event horizon in a finite and perhaps unremarkable time. Two observers, same event, radically different experiences of when. Neither is wrong. Neither is experiencing an illusion. They are both right about their own version of time, and that is the problem. Because if time is different for everyone, if there is no single universal timeline that all events can be mapped onto, if your now is genuinely not my now, then what exactly is time? You might be thinking, all right, this is strange, but surely time is still real. It is just more flexible than Newton thought, a rubber sheet rather than a rigid steel plate, but still a real thing. That would be a reasonable response if the weirdness stopped at relativity, but it doesn't. It barely starts there. Because when you descend from the scale of planets and spaceships and black holes down to the scale of atoms and the particles that make up atoms, a completely different and in many ways even more disorienting picture emerges. At the quantum level, the level of fundamental physics, the equations that describe the behavior of reality stop needing time in the way you might expect. They behave, in certain crucial respects, as though time were irrelevant, and this is not a minor technical quirk. It goes all the way down to the mathematical bones of the theory. Quantum mechanics, the most precisely tested theory in the history of science, describes the world in terms of wave functions, mathematical objects that encode the probabilities of different outcomes for any given measurement. These wave functions evolve according to precise equations, and when you look at those equations, one of the things you notice is something called time reversal symmetry. Almost all of the fundamental equations of quantum mechanics work equally well if you replace time with its negative, if you run the physics backward instead of forward. A particle interaction that can happen in one direction can, at the fundamental level, also happen in the reverse direction. The laws of physics, at the level of individual quantum events, do not care which way time is flowing. They are symmetric. They make no distinction between before and after. This is not a failure of the theory. This is what the theory actually says, confirmed over and over again by experiment. And it raises a question that has haunted physicists for over a century. If the fundamental laws of physics are time symmetric, if the deepest layer of reality has no preferred direction for time, then why do you experience time as having a direction? Why does it feel like time moves from the past to the future and never the other way around? This is known as the problem of the arrow of time, and it is one of the deepest unsolved problems in all of physics. The sensation that time moves forward, that you remember the past but not the future, that broken eggs don't reassemble themselves, that spilled milk doesn't leap back into the glass, that people grow old rather than growing young. All of this has a physical counterpart in what is called the second law of thermodynamics. This law states that in an isolated system, disorder or entropy tends to increase over time. The universe moves from ordered states to disordered states. Glass shatters, smoke disperses, stars burn their fuel and dim, information becomes noise, and this is true. This is real. The universe does appear to be moving in a direction of increasing entropy, but here is the critical, deeply unsettling part. The second law of thermodynamics is not truly fundamental. It is a statistical tendency, not an absolute rule. It emerges from the fact that there are vastly more disordered states than ordered ones, so randomly evolving systems are overwhelmingly likely to move toward disorder. But at the level of individual particles and their interactions, the physics works in both directions. The arrow of time is not carved into the fundamental laws of the universe. It is a statistical artifact. It is something that emerges from complexity and scale, not something that is written into the basic grammar of reality. This means something remarkable and quietly terrifying. The universe at its most fundamental level does not distinguish between yesterday and tomorrow. The asymmetry you experience, the fact that you remember the morning but not the evening, that causes precede effects, that you can change the future but not the past. None of that is written into the deepest equations. All of it emerges from something else, from entropy, from complexity, from the structure of the macroscopic world. The forward flow of time, the thing you are most certain about when you are certain about anything, is a statistical shadow. It is what large-scale complexity looks like from the inside, which means that the directional quality of time, the most viscerally real aspect of your entire experience, is not a feature of fundamental reality at all. It is something that appears at a certain level of complexity and disappears again at the level of fundamental physics. Like the way temperature disappears when you look at a single molecule. Temperature is real, you feel it, but at the level of individual molecules, there is no temperature. There is only kinetic energy, speed, collision. Temperature is what that looks like from far enough away. And some physicists are beginning to suggest that time is the same kind of thing. Real at the level we experience it, invisible at the level of fundamental reality, emergent. A property that exists because of the scale at which we observe the universe, not because it is inscribed in the universe's own foundations. But wait, it gets stranger. Because even if you grant that the arrow of time might be an emergent phenomenon, you might still hold on to the idea that time itself, the bare framework of before and after, earlier and later, is genuinely fundamental. You might say, okay, maybe time doesn't have a preferred direction built into it, but surely the sequence itself, the very fact that there is a sequence, is real. And that is where things get really complicated. Because in 1967, two physicists named Bryce DeWitt and John Wheeler sat down and tried to do something that seemed straightforward. They tried to write an equation that unified quantum mechanics with general relativity. They wanted to describe the quantum state of the entire universe. And what they got, what their equation produced, was one of the most haunting results in theoretical physics. In the Wheeler-DeWitt equation, time does not appear at all. Let that settle in for a moment. The equation that is supposed to describe the quantum state of the entire universe, the most complete description we have attempted of everything that exists, does not contain time as a variable. The universe, described at its most fundamental level by the best framework we have for unifying our two greatest physical theories, appears to be timeless. The equation is static. It describes a universe that does not evolve. It describes a configuration of the universe that simply is, not a universe that was and is and will be, a single, eternal, frozen, everything. Now, you might reasonably object that this seems obviously and absurdly wrong. Things clearly evolve. The universe clearly changes. You clearly experience a sequence. But what the Wheeler-DeWitt equation suggests is that this experience of change, of evolution, of sequence, might be an internal property, something that emerges from the relationships between the parts of the universe, rather than from time flowing through it from the outside. And several serious physicists have spent their careers trying to understand exactly how that could work. One of the most compelling attempts to make sense of this comes from the work of Carlo Rovelli, a physicist at the Centre de Physique Théorique in Marseille, who has thought as deeply about the problem of time as anyone alive. Rovelli's work, developed over decades within the framework of loop quantum gravity, leads to a conclusion that is simultaneously stunning and almost unbearable. Time is not fundamental. It does not exist at the basic level of reality. What we call time is an emergent phenomenon, something that arises from the thermodynamic properties of complex systems, from the relationships between degrees of freedom, and the statistics of large numbers of interacting components. Time, in Rovelli's view, is not the river that everything flows along. It is something more like heat, a property that appears when you have many things interacting in complex ways, and vanishes when you look at the system in enough detail. And Rovelli is not a fringe figure. He is not writing science fiction. His work is taken seriously by serious people, cited in serious journals, engaged with by serious theorists. He is offering what he genuinely believes to be the best available interpretation of what the physics is actually telling us. And what it is telling us is that time, as you experience it, may not be inscribed in the universe at all. It may be something you are generating. This is the kind of claim that needs to be approached carefully, because it is easy to hear it and think it is merely philosophical, a matter of semantics or interpretation, a scientist choosing to describe things in an unusual way, rather than making a substantive claim about reality. But the claim is substantive. It is not that time is just being redefined or relabeled. It is that the standard assumption, the assumption that there is a real external objective flow of time that your subjective experience of time is tracking, may be simply wrong. There may be no flow. There may be no external sequence. There may only be the internal experience, the brain's way of representing to itself the relationships between remembered states and anticipated states, the feeling of being embedded in a process, without any process actually existing in the way you imagine. And to understand why this is more than just philosophy, you need to look more closely at what happens when physicists try to give time an exact definition. Here is something that might surprise you. Despite thousands of years of philosophy, mathematics, and natural science, despite the fact that time is the most fundamental ingredient of almost every physical theory ever written, despite the fact that we measure it obsessively with ever more precise instruments, there is no agreed-upon definition of what time actually is. Ask a physicist to define time precisely and rigorously, and you will get a variety of answers, none of them fully satisfying, many of them circular. Time is what clocks measure. But what is a clock measuring? Time is the dimension along which events are ordered. But what makes one ordering of events the right one? Time is the parameter that appears in the equations of motion. But why does that parameter correspond to the thing you subjectively experience? The definitions collapse into each other or into tautology. The best available definition in physics is something like, time is the coordinate system we use to order events and describe their evolution, which is essentially saying that time is a mathematical tool we use to organize our description of change. And that is a very different thing from saying that time is a real, fundamental feature of the universe that would exist even if no one were there to observe or measure it. The physicist John Wheeler, who co-authored the DeWitt-Wheeler equation, once said something that captures the depth of this confusion beautifully. He said that of all the obstacles in physics, time is the hardest to deal with. He meant this literally. He meant that after a lifetime of working on some of the deepest problems in theoretical physics, including the nature of black holes, the interpretation of quantum mechanics, and the structure of space itself, the one thing he found most resistant to clear understanding was the nature of time. He didn't say this with dismissiveness. He said it with the kind of weight that comes from genuinely grappling with something and finding it genuinely impenetrable. And Wheeler was not alone. Richard Feynman, one of the greatest physicists of the 20th century, famously dodged questions about the nature of time by saying that he could describe what time does mathematically but couldn't tell you what it is. Stephen Hawking, In writing about imaginary time, a mathematical concept he used in cosmology, remarked with characteristic understated irony that it was hard to know which was real, imaginary time or real time, because both were just different ways of describing the universe. These are not expressions of defeat. They are expressions of genuine scientific humility in the face of something that resists being pinned down. And perhaps one of the most striking expressions of that resistance comes from the physicist Julian Barbour, who has spent decades developing a fully worked-out physical theory in which time literally does not exist. Barbour's theory is called timeless physics, and its central argument is deceptively simple. The universe is not a movie, a sequence of frames, each one following the other in time. The universe is a single, complete, static mathematical object. What we experience as time is actually something he calls the now, a succession of different configurations of the universe, each of which carries within it records and memories that make it feel like it is part of a sequence. But there is no sequence. There is only a collection of what Barbour calls nows, each one complete and static, each one containing what appears to be a history, without any actual history existing. Think of it this way. Imagine a long book in which every page contains a description of a moment. Each page also contains descriptions of what the characters remember from previous pages. Now imagine that the book has no order. The pages are just there, static, simultaneous, none more present or more real than any other. The experience of reading the book, moving through it page by page, is something you impose. The book itself just is, all at once. Barbour is suggesting that this is, in a deep sense, a more accurate description of the universe than the movie metaphor. Not because he wants to be provocative, but because the mathematics points in this direction. Barbour's idea might sound purely speculative, but it connects to something very concrete in physics, the problem of time in canonical quantum gravity. When physicists try to apply the rules of quantum mechanics to the universe as a whole, including space itself as a quantum system, they consistently run into the Wheeler-DeWitt equation and its terrifying implication. The wave function of the universe does not evolve, it is static. The universe at its deepest quantum level does not change. There is no time in the equation. Something about this result feels impossibly wrong, and yet it keeps emerging. Different approaches to quantum gravity, different mathematical frameworks, different starting assumptions, they all seem to converge on the same uncomfortable conclusion. Time, at the most fundamental level, disappears. It is not reduced or modified or bent, it vanishes. And that should give you pause. That should lodge itself somewhere in the back of your mind as you go about your day, feeling time tick past you with such magnificent, convincing reliability. Now here is where the narrative branches into something even more unsettling. Because everything we have talked about so far, the relativity of time, the time symmetry of quantum mechanics, the arrow of time problem, the Wheeler-DeWitt equation, all of it can be framed, at least loosely, as a technical problem. A problem within physics, about how to properly describe and understand time using the tools of physics. But there is a completely different angle on this question, coming not from physics but from neuroscience and cognitive science, and it suggests that the problem runs even deeper than the physics suggests. Because what neuroscience is discovering about how your brain constructs your experience of time is, in its own way, just as disorienting as anything that comes out of quantum gravity. It suggests that the vivid, immediate present tense feeling of being in time right now is something your brain assembles after the fact, using a combination of memory, prediction, and neural processing that operates on timescales you are completely unaware of. Consider this experiment. Neuroscientists have demonstrated repeatedly, through careful measurement, that the neural processes associated with a conscious decision to move, say, to flex your finger, actually begin in the brain several hundred milliseconds before you consciously experience making the decision. The neural preparation for the action precedes your subjective sense of choosing to act. This was first demonstrated by the neuroscientist Benjamin Libet in the 1980s and has been replicated and extended in various forms many times since. The precise interpretation of Libet's experiments is still debated, and some researchers argue that later experiments have complicated the original picture. But the core finding, that your conscious experience of choosing, of being the author of an action in the present moment, does not align perfectly with the underlying neural timeline, is real and documented. What you experience as happening now is not necessarily what is happening now in terms of the neural computations that give rise to that experience. Your brain imposes a narrative of present tense agency on a process that has a different and less neat timing in the underlying biology. This is part of a larger picture that neuroscience has been building over the past several decades. The idea that your conscious experience is not a live feed, it is an edited broadcast. Your brain receives a vast torrent of sensory information from your eyes, your ears, your skin, your internal organs, and it processes all of this information asynchronously, in parallel, at different speeds, through different neural pathways. Light is processed differently from sound. Touch reaches different brain regions at different speeds. If your experience of the present moment were truly real time, it would be a chaos of slightly offset streams, a cacophony of misaligned signals. But you don't experience that. You experience a seamless, coherent, present tense reality, which means your brain is doing something. It is holding on to incoming information, buffering it, aligning the streams, filling in gaps, correcting for timing differences, and then presenting you with a unified, coherent version of what is happening, stamped with the feeling of being in the now. The now you experience has a duration. It is not a mathematical point in time. It is typically a window of a few hundred milliseconds to a few seconds, sometimes called the specious present, within which your brain bundles events together and presents them to you as simultaneous, as happening at the same time, even if they did not. Your now is manufactured. It is a product. It is the output of a neural construction process, not a transparent window onto the real present moment, and the construction goes deeper than just the present moment. Your experience of duration, of how long things take, is wildly unreliable and deeply context-dependent. Time passes slowly when you are bored and fast when you are engaged. It stretches in moments of fear and contracts in moments of flow. Your memory does not preserve temporal spacing accurately. Two events from last year might feel equally distant even if one happened in January and the other in October. Distant events from childhood feel compressed in memory, as though they are all clustered together in a vague, undated past, while recent events feel spread out with more texture and spacing. Your brain's representation of time is not a faithful recording. It is a reconstruction, subject to all kinds of biases and distortions, shaped by emotional significance, by how often you have revisited a memory, by how distinctive the event was, by the state you were in when you encoded it. The timeline of your life is not a straight line that you faithfully recall. It is a story you are constantly re-editing, using incomplete and partially fabricated source material. This raises a question that is worth sitting with. If your experience of the present moment is constructed, if it has a duration and a built-in smoothing process, and a post hoc narrative of agency, and if your experience of the past is reconstructed and unreliable and subject to revision, and if your experience of the future is imagined, which is to say generated by your brain through predictive modeling rather than perceived through any direct mechanism, then what exactly is the foundation of your certainty that time is real? Your certainty about time is not based on direct perception of something external. It is based on an internal experience. And that internal experience is, as we have just seen, assembled by your brain using processes that have their own timing, their own delays, their own corrections and distortions. You are not perceiving time. You are experiencing your brain's model of time. And your brain's model of time was built by evolution to serve survival, not to accurately represent the fundamental structure of the universe. Think about what that means. Evolution optimized your sensory and cognitive systems to keep you alive and reproducing in a specific ecological niche on the surface of a particular planet, at velocities far below the speed of light, in gravitational fields far below those near black holes. Your brain was not built to accurately perceive time at the quantum scale, where time symmetry reigns. It was not built to notice the time dilation that occurs at relativistic speeds, because your ancestors never traveled at relativistic speeds. It was not built to grapple with the Wheeler-DeWitt equation or with Barber's timeless universe or with Ravelli's emergent time. It was built to model a macroscopic world of objects and threats and opportunities, and to represent that world in a way that allows you to act quickly and effectively. The sense of time flowing from past to future is extremely useful for that purpose. A predator that appears in your environment right now is more immediately relevant than one that appeared yesterday. The ability to remember the past and anticipate the future is crucial for planning and learning. Time, as your brain constructs it, is a fantastic tool for navigating the world your ancestors evolved in. But a tool built for a specific purpose is not the same as an accurate representation of fundamental reality. And when we build instruments that can probe deeper than our evolved senses, instruments like particle accelerators and telescopes, and precision atomic clocks, what those instruments tell us about time is deeply, persistently, and specifically inconsistent with the intuitive model your brain is running. There is a concept in physics and philosophy that helps frame this precisely: the distinction between ontology and phenomenology. Ontology is about what actually exists, what is real, what is out there independently of any observer. Phenomenology is about experience, about how things appear to a perceiving consciousness. For most of human history, we assumed that our phenomenological experience was a reliable guide to ontology, that the way things appeared to us was a reasonable approximation of the way they actually were. This assumption has been progressively undermined by science. The solid, continuous, color-filled world you perceive is ontologically a vast emptiness, punctuated by particles separated by enormous relative distances, with no intrinsic color, the colors being a product of how your visual cortex processes specific wavelengths of electromagnetic radiation. The smooth, curved edges you see in objects are the product of your visual system's interpolating behavior, and ontologically, those objects are made of atoms arranged in discrete ways. The silence you hear in a room is ontologically filled with electromagnetic radiation across a wide spectrum, most of which your auditory system cannot detect. In each of these cases, what you experience and what exists are not the same thing. Your experience is a model, a useful, simplified representation of an underlying reality that is more complex and less intuitively accessible. And what physics is increasingly suggesting is that time, the most fundamental element of your experience, may follow exactly the same pattern. What you experience as time may be a model, a useful representation built by your brain, of an underlying reality that either has no time or has something so different from your intuitive notion of time that time is barely even the right word for it. The model of the block universe is the version of this that most physicists take seriously. The block universe, sometimes called eternalism, is the view that follows most naturally from Einstein's theory of special relativity. It holds that past, present, and future all exist simultaneously and equally. The universe is a four-dimensional block of space-time, in which every event that has ever happened and every event that will ever happen is simply there, located at its specific position in the four-dimensional geometry, no more or less real than any other event. Your birth is there, at its coordinates. Your death is there at its coordinates, already fixed, already real, waiting for your experience to move along the trajectory through the block that your path through space-time describes. What you experience as the passage of time, as the present moment advancing into the future, is, on this view, an artifact of your consciousness moving along your world line through the block, the way a point of light moves along a film strip. Each individual frame of the film strip is static. The film doesn't flow. The projector creates the impression of flow by moving through the frames in sequence. Your consciousness is the projector. The film is already complete, all of it, from the Big Bang to whatever final state the universe reaches. The block universe is not a fringe idea. It is probably the majority view among physicists who think carefully about the implications of relativity. It is the view that falls most directly out of the mathematics when you take Einstein's equations seriously. The relativity of simultaneity, the fact that two observers in different states of motion disagree about what is happening right now at distant locations, implies that there is no global present, no single privileged now, which in turn implies that the present is not a special moment in the universe's evolution. Past, present, and future are equally real. The block is all of it, and your experience of the present moment is simply your subjective position within the block, like a bookmark placed in a novel. The novel doesn't care where the bookmark is. The novel exists in its entirety, all its pages and all its words, whether you are reading it or not. The experience of reading is sequential. The existence of the novel is not. And if the block universe is correct, then the implications are vast and deeply disorienting. The most immediate one is this: there is no such thing as becoming. Nothing comes into existence. Nothing passes out of existence. Every moment that has ever been or will ever be is frozen in place in the block, equally real, equally present in some absolute sense, even if your experience moves through them in sequence. Your past self is not gone. They are simply located at different coordinates in the block than you are right now. The moment of your birth is still there, still happening, in the only sense that matters to physics. It exists at its location in four-dimensional space-time. The moment of your death is already there, not waiting to happen, not yet to be, but already real, already fixed in the geometry of the universe. The word future is actually misleading because it implies that future events don't yet exist, but in the block universe, they do. They just exist at coordinates that your experience hasn't reached yet. And the word past is misleading because it implies that past events are gone, But they are not. They exist at coordinates that your experience has already passed through. The universe doesn't have a past and a future. It has a four-dimensional structure in which all events are co-present, spread out across the block like stars spread across the night sky, each one exactly where it is, none more real or more present than any other. Now you might feel a very specific kind of resistance rising as you process this. You might be thinking, but I can affect the future. I can make choices. The future is open. The past is closed. There is an asymmetry there that is real, that matters, that is part of what makes life meaningful. And this is where the block universe collides with one of the most cherished and deeply personal human concepts, free will. If the future already exists in the block, if your death is already there at its coordinates, if every decision you will ever make is already inscribed in the four-dimensional structure of the universe, then in what sense are you actually choosing anything? In what sense is your deliberation about what to do next anything more than the unfolding of a process that is already determined, already complete in the block, already fully real? The feeling of choosing, of standing at a crossroads and genuinely deliberating and then acting, would then be, on this view, something like the feeling of a point moving along a line that is already drawn. The motion feels real. The line was always there. This doesn't mean that free will is simply an illusion in some crude and dismissible sense. The reality of your experience is not canceled out by its underlying mechanics. But it does mean that the relationship between your subjective experience of choosing and the physical reality underlying that experience may be stranger than anything your intuitive model can accommodate. The block universe suggests that the feeling of standing at a crossroads in the present, with the future genuinely open, is a kind of cognitive artifact, a consequence of having a memory of the past and no memory of the future, which creates the experience of standing at the edge of the unknown. But the unknown is only unknown to you. It is not truly open. It is already fully real. The future is not waiting to be written. It has already been written. You are simply reading it for the first time, under the illusion that you are the one holding the pen. And this connects to something even more fundamental than free will. It connects to the nature of causality itself. Causality, the principle that causes precede their effects, that the past shapes the future and not the other way around, is one of the most basic assumptions underlying not just science, but all rational thought. Every time you reason about why something happened, every time you trace an outcome back to its origins, every time you make a plan based on the assumption that your actions today will have consequences tomorrow, you are relying on causality. You are assuming that the arrow of time is real, that before and after are not just labels but genuinely different kinds of moments, with the before having a specific kind of power over the after that the after does not have over the before. But if the fundamental laws of physics are time-symmetric as we established earlier, then causality is not inscribed in those laws. It is another emergent property, another feature that appears at the macroscopic scale but dissolves when you look closely enough. And some physicists and philosophers have gone further, arguing that even at the macroscopic scale, causality is not as solid as it feels. That it is, in part, a story we tell about correlations between events, a narrative we impose on a universe that contains correlations without necessarily containing causes in any deep metaphysical sense. The quantum world adds yet another layer of trouble to causality. In standard quantum mechanics, the behavior of individual particles is genuinely probabilistic. When a radioactive atom decays, there is no prior state of the atom that determines exactly when it will decay. The decay happens at a random time, drawn from a probability distribution. Nothing causes it to decay at the specific moment it decays, at least not in the traditional sense of cause. There is no fact about the state of the atom that makes the decay happen at time t, rather than time t plus 1 second. It is genuinely, irreducibly random. This is not a statement about our ignorance, about some hidden information we don't yet have access to. It is, according to the standard interpretation of quantum mechanics, a statement about the world. The world is genuinely indeterminate at this level. Events happen without specific prior causes, and this means that even at the quantum scale, the sense in which causes reliably produce specific effects in which the past determines the future is not absolute. It is only statistical, only approximate, only something that emerges from large numbers of random events washing out into predictable averages. But wait, there is something even stranger waiting in the quantum world, something that does not just complicate causality, but seems to twist it into a shape that ordinary language can barely describe. It is quantum entanglement, and it is one of the most thoroughly verified and deeply puzzling phenomena in all of physics. When two particles interact in certain ways, they become entangled. After that, measuring a property of one particle instantly determines the corresponding property of the other, regardless of the distance between them. You can separate the two particles by billions of light years. The moment you measure one, you instantly know what you would find if you measured the other. This has been tested experimentally, repeatedly, in increasingly sophisticated ways, and the results are unambiguous. The correlations are there. They are real. They cannot be explained by any information exchanged between the particles, because the correlation occurs instantaneously, faster than any signal could travel between them, even at the speed of light. Einstein hated this. He called it spooky action at a distance, and spent years trying to find a way to explain it away, through what are called hidden variables, some deeper level of reality, where the outcome was already determined before the measurement. But Bell's theorem, proved in 1964 by physicist John Bell, and subsequently tested experimentally with extraordinary precision, showed that Einstein's hope was unfounded. The correlations in entanglement cannot be explained by any hidden variables of the classical type. The universe really is non-local in this sense. The correlations really are instantaneous across any distance. This does not mean you can use entanglement to send information faster than light, which would violate relativity in a straightforward way. The no-communication theorem ensures that the random outcomes of quantum measurements cannot be used to transmit a message. But the correlations themselves, the fact that measuring one particle instantaneously affects what you would find if you measured the other, even when the two are space-like separated, meaning no signal traveling at or below the speed of light could possibly connect them, suggests that the universe has a structure that is not fully captured by any picture of local events connected by causal chains propagating through time. Something is connecting these particles across space without any time-respecting causal mechanism, something that is either outside time or indifferent to it. The universe, at its quantum level, is not a collection of isolated events connected by causal chains marching forward in time. It is something more like a web of correlations, a network of relationships that span space and time in ways that don't respect the intuitive picture of causality that your macroscopic brain evolved to navigate. And there is a direction in physics that takes this even more seriously, that tries to build a picture of the universe in which space and time are not the fundamental background, but emergent phenomena that arise from something even more basic, something that has no inherent geometry, no inherent locality, no inherent temporal structure. This approach goes under various names: amplitude-hedron physics, it from qubit, holographic approaches to quantum gravity, and while these are technically diverse research programs, they share a common intuition. Space and time are not the bedrock, they are the surface. Underneath them is something that does not have these properties, something from which space and time emerge the way temperature emerges from molecular motion, as a large-scale statistical description of something that, at the fundamental level, is entirely different. The amplitude-hedron is particularly striking in this context. It is a geometric object, discovered by physicists Nima Arkani-Hamed and Jaroslav Trnka in 2013, that encodes the probabilities of particle interactions in a way that completely bypasses the framework of spacetime. In the traditional way of calculating particle interaction probabilities using Feynman diagrams, you build up the answer step by step, tracking particles as they move through space and interact at specific points in time. It is an explicitly spacetime-based calculation. The amplitude-hedron approach produces the same answers, but without any reference to space or time at all. The geometry of the amplitude-hedron, which lives in a purely mathematical space with no relation to physical spacetime, encodes all the information about the interaction. Spacetime in this picture is not even an input. It is an output, something that emerges from the geometry of this more fundamental mathematical object. Arkani-Hamed has been explicit about what he thinks this means. He has said that spacetime, the stage on which we think all of physics is played out, is not fundamental. It is emergent. And if spacetime is emergent, then time, as a component of spacetime, is emergent too. The holographic principle, which arose from work on black holes by Stephen Hawking and Jacob Bekenstein, and was developed into a precise theoretical framework by Juan Maldacena in 1997, points in a similar direction. Maldacena's insight, known as the ADS-CFT correspondence, showed that a complete description of the physics inside a region of space, including all its gravitational dynamics, could be encoded in a quantum field theory living on the boundary of that region, a theory with one fewer spatial dimension and, crucially, no gravity. This is not a metaphor or an analogy. It is a precise mathematical duality. The interior of the space and the boundary are equivalent descriptions of the same physical system. The three-dimensional interior, including all of its gravitational dynamics, all of its space-time geometry, emerges from a two-dimensional boundary theory. The interior's spatial and temporal structure is not fundamental. It is a holographic projection of a boundary theory that does not contain it in an obvious way. Gravity, space, time, all of these emerge from a lower dimensional description. They are real in the sense that they are accurate descriptions of what you would observe if you were inside the space. But they are not fundamental. They are derived. They are what the boundary theory looks like from a certain vantage point. Take a moment with this. The three-dimensional world you inhabit, with its spatial extension and its temporal flow and its gravitational fields and its sense of depth and duration, may be the holographic projection of a two-dimensional reality that doesn't contain space or time in the form you recognize. You may be living inside the hologram, not in the science fiction sense, not in the simulation sense yet, but in the deep physical sense that the dimensionality and structure of your experience may be an emergent property of a lower dimensional, potentially timeless fundamental description. The world you navigate every day may be the shadow of something else, something with fewer dimensions and less obvious structure, from which the familiar world crystallizes as an emergent phenomenon. This is not speculation dressed up as science. This is a mainstream research program in theoretical physics, backed by the most precise and technically sophisticated mathematical work that physics has produced in the last 3 decades, and it consistently, repeatedly, from multiple independent angles, points toward the same conclusion. Time at the fundamental level is not there, but perhaps the most philosophically vertiginous aspect of all of this is what it does to the concept of now, the present moment, the immediacy of your current experience, the specific feeling of being here. Reading these words in this moment seems like the most unassailable thing in existence. Whatever else might be doubtful, whatever other aspects of reality might be questioned, this moment, this immediate, vivid, present tense experience feels absolutely real. Descartes built his entire philosophy on something like this. Whatever I might doubt, I cannot doubt that I am doubting, that there is experience happening here, now. The present moment seemed like the one undeniable anchor, but what we have been building toward suggests that this anchor is not where you think it is. The now you experience is assembled by your brain from information that arrived at different times. It is a constructed window with a duration of hundreds of milliseconds, not a geometric point. It is relative in the sense that Einstein showed that simultaneity is relative to the observer's state of motion, and it may be entirely absent from the fundamental description of the universe, replaced by a timeless block in which all moments are equally real, or by a deeper structure in which moments themselves don't exist. The present moment is the most real thing in your experience. It may be one of the least real things in the universe. And now consider what happens to the concept of identity when you take all of this seriously. Your sense of being a continuous, persisting self, a person who existed yesterday and exists today and will exist tomorrow, the same person across time, is built on the assumption that there is a time through which you persist. If time is not fundamental, if the block universe is correct and all your temporal stages coexist equally in the four-dimensional structure of the universe, then the you that exists right now is not the same you that existed 10 years ago in the sense of being a continuous thread. It is a different slice of the block. You and your past self are not connected by an ongoing process of continuation. You are both just there, at different coordinates, related by certain structural continuities in the pattern of matter and information, but not literally connected by a flowing time. The story of you, the narrative of a person who began somewhere and is going somewhere, is exactly that, a story. A representation your brain generates to make sense of the pattern of slices in the block. The you of 10 years ago is as real and as present in the block as the you of right now. Neither is more current, neither is more here. The feeling of being in the present, of being the current version of yourself, is not a metaphysical fact about the universe. It is a feature of your subjective perspective within the block. This connects in a deep way to the Buddhist philosophical tradition, which reached some of these conclusions through a very different method, through careful phenomenological investigation of experience, rather than through mathematical physics, and arrived at a remarkably similar place. The Buddhist doctrine of momentariness holds that the self is not a persistent entity, but a sequence of momentary experiences, each one arising and passing, none of them constituting a permanent underlying substance. The feeling of being a continuous self is, in this tradition, a kind of cognitive fiction. a pattern that the mind projects onto the stream of experience to create the sense of a coherent subject moving through time. The doctrine of impermanence, one of the three marks of existence in Buddhist philosophy, holds that all phenomena, without exception, are transient, that nothing persists, that everything arises and passes away. These insights, reached through contemplative practice thousands of years ago, are strikingly resonant with what physics is now suggesting through an entirely different route, that the persistence you feel, the continuity you take for granted, is a model your mind imposes on a reality that may be fundamentally different, fundamentally more fragmented, fundamentally less continuous than your experience suggests. The simulation hypothesis enters this territory naturally, though you should be careful about how seriously to take it as a scientific claim, as opposed to a philosophical thought experiment. The simulation hypothesis, most popularly associated with philosopher Nick Bostrom's 2003 paper, and more recently with various public intellectuals and technologists, suggests that what we call reality might be a computational process running on some kind of substrate, and that time, space, and physical law might be features of the program rather than features of ultimate reality. The appeal of this idea in the present context is that it offers an intuitive model for how time could be emergent without being fundamental. In a simulation, time is a feature of the computational process, not of the substrate. The substrate just runs through operations. Time, as experienced by entities within the simulation, is the order of those operations as experienced from the inside. Whether or not the simulation hypothesis is literally true, it offers a useful conceptual template. It shows how you can have a world in which time is internally real and operationally indispensable, while being ontologically derivative, a feature of the process rather than a feature of what the process runs on. And here is something that should give the simulation hypothesis at least a degree of serious consideration beyond mere speculation. The universe, as far as physics can tell, is deeply mathematical. Not just that mathematics is useful for describing the universe, but that the universe appears to be constituted by mathematical relationships. The physicist Max Tegmark has argued, in his mathematical universe hypothesis, that the universe is not just described by mathematics but is itself a mathematical structure, that physical existence and mathematical existence are the same thing. If you take this seriously, then the question of whether time is real becomes the question of whether time is a fundamental feature of the mathematical structure that the universe is, or whether it is a derived feature, something that emerges within the structure rather than being part of its foundational axioms. And as we have seen from multiple directions, the evidence leans heavily toward the latter. Time keeps disappearing from the fundamental equations. It keeps emerging at higher levels. It keeps behaving more like temperature than like position, more like an approximation than like a fact, more like a tool than like a truth. There is a fascinating thought experiment that helps to crystallize the strangeness of this conclusion. Imagine a universe consisting entirely of two particles interacting with each other. There is nothing else. No background space, no reference objects, no external observer. Now ask, is there time in this universe? According to Ravelli's relational interpretation of quantum mechanics, time in this universe would be nothing more than the changing relationship between the two particles. There would be no time without the change. There would be no change without the two particles affecting each other. Time would not be a container in which the particles exist. Time would be a way of describing how the particles relate to each other as they interact. Change the particles, change the interaction, and you change time. Remove the particles entirely, and there is no time. In this picture, time is not a thing. It is not even a property of things. It is a relationship between things, a way of measuring and describing the changing configurations of a physical system. Extend this picture to the universe as a whole, and you get Ravelli's view. Time, for the universe taken as a totality, is undefined. The universe does not have a time in the way a particle within the universe has a position. Time only makes sense for subsystems of the universe, as a way of describing how those subsystems change relative to each other and relative to everything else. There is no time for the universe, because there is nothing outside the universe for it to change relative to. This might sound like a subtle technical point, but its implications are enormous. If time only exists as a relational property of subsystems within the universe, then the kind of time that science has always assumed as a backdrop, Newton's absolute time, or even Einstein's curved space-time, is a secondary phenomenon. It is what appears from inside the universe, from the perspective of one part of it looking at another. A bird inside a forest can describe the relative positions and movements of the trees, but the forest does not move relative to anything. because there is nothing outside the forest for it to move relative to. Ask where the forest is moving to, and the question becomes meaningless. Similarly, Ravelli argues, ask when the universe is. Ask what time it is in the universe as a whole, and the question becomes meaningless. Time is internal, it is relational, it is perspectival. It is not a feature of the universe from the outside, because there is no outside. And this is not a failure of our current theories. This is what the theories taken seriously actually predict. Let us now follow the implications into the domain of cosmology, into the question of how the universe began and what that means for the nature of time. The Big Bang, the event approximately 13.8 billion years ago from which the observable universe emerged, is typically described as the beginning of time, as well as the beginning of space and matter. Stephen Hawking and Roger Penrose proved theorems showing that, under certain reasonable conditions, the history of the universe cannot be extended backward beyond the Big Bang, that the Big Bang is a genuine singularity in the mathematical structure of space-time, a point at which the equations break down and all of physics as we know it ceases to apply. This is often interpreted as meaning that there was no time before the Big Bang, that the question, what happened before the Big Bang, is like asking what is south of the South Pole, a question that seems meaningful, but actually has no referent. There is no south of the South Pole because the South Pole is the boundary of that coordinate system. There is no before the Big Bang because the Big Bang is the boundary of time. But here is where things get philosophically treacherous. If the Big Bang is the beginning of time, then time has a beginning. It came into existence. Something that comes into existence is not fundamental. Fundamental things don't come and go. They simply are. A truly fundamental feature of reality would not have a boundary, a point before which it didn't exist. The fact that time had a beginning, if the standard cosmological picture is correct, is itself evidence that time is not fundamental, that it is something that emerges within the universe, rather than something the universe exists inside. And there are cosmological models, speculative but seriously entertained by physicists, in which time is even more obviously emergent. In Hartley and Hawking's no-boundary proposal, for example, the early universe is described using imaginary time, a mathematical trick in which the time coordinate is treated as a spatial coordinate, making the universe's boundary smooth rather than singular. In this description, asking for the moment of creation is again like asking what is south of the South Pole. But the interesting thing is that in the no-boundary proposal, time as you know it, real time, the kind that flows and creates the experience of before and after, only fully emerges as the universe expands and cools. It crystallizes. It solidifies from something more fluid and less definite. The distinction between time and space becomes sharp only as the universe evolves. Near the beginning in the no-boundary proposal, time and space are on equal footing, neither more fundamental than the other, neither having the distinctive directional asymmetric quality that characterizes the time you experience. Time, in this picture, is something the universe acquires, like a symmetry that breaks as a system cools. The distinction between time and space, the quality that makes time feel different from the three spatial dimensions you move through, is a feature that emerges at a certain phase of the universe's evolution. Before that phase, there is no time in any meaningful sense. There is just a smooth, curved, four-dimensional geometry without a preferred direction. This picture of time crystallizing from a more symmetric state connects to broader ideas in physics about symmetry breaking and the emergence of structure. The universe, at the moment of the Big Bang and immediately after, was in an extremely symmetric state. All forces were unified. All particles were equivalent. The distinctions we see in the current universe between different types of particles, different forces, different structures, all of those emerged as the universe cooled and various symmetries broke, creating the differentiated world we inhabit. The distinction between matter and antimatter emerged this way. The distinction between the different fundamental forces emerged this way. And it is possible, perhaps even likely in the view of some physicists, that the distinction between time and space, and the asymmetric, directed quality that makes time feel so different from space, also emerged this way, as a broken symmetry, a feature that crystallized from a more symmetric early state, in which case the time you experience is not eternal and universal and fundamental. It is a local feature of a specific phase of the universe's evolution, a phase that has lasted for about 13.8 billion years and may not last forever. The arrow of time may be a broken symmetry, like so much else in the universe, and what it was before it broke, the universe in that more symmetric state, is something that time as we know it is simply not equipped to describe. Consider for a moment what it would mean to actually live with this knowledge, to truly internalize it, rather than just processing it intellectually, not just to know it as a fact in the way you know the capital of France, but to feel it, to carry it around in your body, to let it reshape the texture of your experience. What would it feel like to walk through your day knowing that the present moment is a construction, that the past is a collection of records rather than a receding reality, that the future is either already fixed in the block or not a temporal fact at all, that the flow you feel is not a feature of the universe but a feature of your perspective within it? This is not an easy thing to sit with. The human mind did not evolve to find this comfortable. You are built to act as though time is real and flowing, and to care about the future, and to remember the past, and to feel the urgency of the present moment. These are not optional settings you can switch off. They are deep features of the operating system. But there is a specific kind of vertigo that comes from holding two levels of reality simultaneously: the operational level at which time is real and matters and structures everything, and the deeper level at which time may be an artifact, a useful fiction, a compelling approximation of something else. It is the vertigo of a building that looks solid from the street, but which, if you could see the molecular level, is mostly empty space. The building doesn't fall, but your sense of what it is has changed forever. There are scientists and philosophers who find this liberating. Carlo Rovelli, whose work on timeless physics we have already discussed, writes about the dissolution of time with something approaching joy, or at least acceptance. The acceptance of someone who has looked at reality clearly and found that it is stranger and more interesting than the familiar version. Rovelli argues that once you let go of the idea of time as a fundamental given, once you accept that what you experience as time is a perspective, a thermodynamic shadow, you are freed from a certain kind of illusion about your place in the universe. You are freed from the sense that you are flowing toward something, that you are in a race that has a specific direction. You can be here, in the timeless sense of here that physics suggests is the only sense, without the anxiety of a timeline. There is something almost Buddhist about this response, a recognition that the urgency you feel about time, the constant pressure of before and after, is a product of your perspective rather than an objective feature of the universe, and that releasing that perspective, if only partially and provisionally, might reveal something more spacious and less fraught. But for many people, the response to these ideas is the opposite of liberation. It is a specific and deep unease that is hard to name precisely. Not quite fear, not quite sadness, but something in between, a kind of ontological vertigo that comes from having the most basic assumption of your existence destabilized. If time is not real, then what exactly are you? A pattern in a timeless block? A sequence of configurations in a thermodynamic gradient? A holographic projection of a two-dimensional boundary theory? These descriptions are not wrong, but they are not the same as being a person moving through a life. They are the view from outside human experience, looking at the physics, and the physics does not see you the way you see yourself. The physics sees a pattern of matter and energy evolving according to equations that don't need you to feel anything, don't need you to be anywhere specific in time, don't need the present moment to be special. The physics is indifferent to your experience of being here now, reading these words, feeling this specific quality of present tense awareness. And that indifference is, in its own way, one of the most disturbing things that physics has to offer. And yet the experience persists. Whatever the physics says, you are here. Whatever the block universe contains, you are in this moment. And it feels like the only moment, the real moment, the moment that matters. And this is perhaps the deepest tension in this entire inquiry. The gap between the physics and the phenomenology, between what the equations say and what the experience is, cannot be closed by simply declaring that the experience is an illusion. Illusions are still experiences. The fact that the horizon is not actually where it appears to be does not make the appearance of the horizon less real as an appearance. The fact that your experience of time may not accurately represent the fundamental structure of the universe does not make the experience less real as an experience. You are genuinely experiencing something. The question is, what that something actually is, what it is tracking, what its relationship to the physical world really consists of. And that question, the hard problem of consciousness applied to time, is not answered by saying that time is emergent or that the block universe is correct. It just becomes deeper and more mysterious. The hard problem of consciousness, as formulated by philosopher David Chalmers, is the problem of explaining why there is any subjective experience at all, why there is something it is like to be a physical system, why the information processing that happens in your brain gives rise to an inner life rather than just happening in the dark. This problem is hard in the specific technical sense that no amount of explaining the functional and physical processes of the brain seems to close the gap between the physical description and the experiential reality. You can describe every neuron and synapse and neurotransmitter and electrical potential in exhaustive detail, and still not explain why any of it feels like anything. Consciousness is the one thing in the universe that refuses to be fully externalized, fully described from the third-person perspective that science uses for everything else. And time, as experienced from the inside, is one of the most fundamental and ineliminable features of consciousness. The flow of time, the nowness of now, the directionality of experience from memory to anticipation, these are not peripheral features of consciousness. They are not optional add-ons. They are the very structure of experience. To be conscious is, in part, to be in time, to have a present moment, to remember a past and anticipate a future. Take away the temporal structure of consciousness, and you haven't just removed one feature among many. You have removed something that looks very much like the container that consciousness happens in, which raises a question that sits right at the intersection of physics and philosophy and cognitive science, and manages to be uncomfortable in all three domains simultaneously. What if consciousness and time are not just correlated but deeply, fundamentally linked? What if the experienced flow of time is not a side effect of consciousness, not just a feature that consciousness happens to have, but is in some way constitutive of consciousness itself? What if being a conscious entity just is, in part being a system that generates a sense of temporal flow, not as an accurate perception of the external world, but as the internal logic of what it means for there to be an inside view at all? This is not a mainstream position in physics, but it is a position that some very serious thinkers have entertained. Roger Penrose, one of the most distinguished mathematical physicists alive, has argued in his books that consciousness involves processes that go beyond conventional computation, and that these processes may be connected to the quantum gravitational level of physics, precisely the level at which time seems to dissolve. His collaborator, the anesthesiologist Stuart Hameroff, has proposed that quantum processes in the microtubules of neurons might be the site of these consciousness-related processes, and that the collapse of the quantum wave function, which is one of the places in physics where time seems to play a genuinely asymmetric role, might be connected to conscious experience. The Penrose-Hameroff proposal is controversial and unproven, but it points to something real: the fact that consciousness and the problems of time in physics both resist standard explanatory frameworks, and both involve processes at or near the boundary between the quantum and classical worlds. There is a thought that emerges naturally from all of this, a thought that is simultaneously very simple and very hard to fully absorb. If time is emergent, if it arises from the relationships between things rather than being a background in which things exist, then in a universe with no observers, no complex systems, no thermodynamic gradients, no brains and no consciousness, there might be no time in any meaningful sense. The universe might be, without observers, a timeless mathematical structure, static and eternal and complete. Time might be something that happens when complex systems capable of storing information about the past and modeling the future, systems like brains, emerge within the universe. Time might be, in the most literal sense, something we bring to the universe, not something we perceive, not something we are embedded in, something we create. The universe does not have a before and after until something arises within it that can register a before and after. The universe does not move from past to future until something arises within it that can remember and anticipate. The flow of time might be, in this view, as much a property of minds as it is a property of the universe. It might be the universe's way of experiencing itself through the medium of conscious beings embedded within it, beings who are complex enough to impose a temporal structure on the timeless mathematical fact of their own existence. This idea, taken seriously, changes the relationship between consciousness and the physical world in a way that most physicists are deeply uncomfortable with. Physics, as a discipline, is built on the assumption of a mind-independent reality, a world that would be exactly what it is whether or not anyone were observing it, and the task of physics is to describe that world accurately, bringing consciousness into the ontology, making it not just an emergent feature of complex matter but something that plays a role in constituting reality, crosses a line that most physicists prefer not to cross. And yet the intersection of quantum mechanics and consciousness is precisely the territory where that line is hardest to maintain. The measurement problem in quantum mechanics, the question of why quantum systems seem to be in superpositions of different states until they are measured, at which point they collapse to a definite state, is one of the deepest unresolved problems in physics, and many of its proposed solutions involve, in one way or another, the observer, the measuring apparatus, or in some interpretations, consciousness itself. The role of observation in quantum mechanics is not fully understood. The relationship between the quantum description of a system and the experienced reality of a measurement outcome is not fully understood, and time, in quantum mechanics, is one of the places where this tension is most acute, because the collapse of the wave function, if it is a real physical process, involves a genuine temporal asymmetry, a before and an after, even though the Schrödinger equation that governs the wave function's evolution is time-symmetric. Something is introducing a temporal asymmetry at the moment of measurement. Something is creating a before and after. Something is making the present special, and no one knows exactly what that something is. The many worlds interpretation of quantum mechanics, developed by Hugh Everett in 1957 and taken increasingly seriously by physicists and philosophers of physics, offers one radical way out of this problem. In the many worlds interpretation, there is no collapse. The wave function never collapses. Every time a quantum measurement is made, every time a system that is in a superposition interacts with a measuring apparatus, the universe branches. Both outcomes happen. The universe splits into two branches, one in which the first outcome occurred and one in which the second outcome occurred. Every quantum event that could go multiple ways creates a branching, and the universe becomes an ever-expanding tree of branches, with every possible quantum history playing out in some branch. You, in this picture, are only in one branch at a time, which is why you only ever see one definite outcome. But your counterpart in another branch saw the other outcome, and is every bit as real as you are. There are, in the many worlds picture, an almost incomprehensible number of parallel versions of reality, all equally real, all evolving simultaneously, according to the time-symmetric Schrödinger equation, none of them privileged, none of them the real one. The many worlds interpretation has a strange relationship with time. On one hand, it restores time symmetry at the fundamental level, because there is no collapse, no irreversible event, just the deterministic, time-symmetric evolution of the universal wave function forever. In this sense, it is cleaner than standard quantum mechanics, which has the time asymmetric collapse as an unexplained primitive. On the other hand, the branching of the wave function is itself an irreversible process from the perspective of any given branch. Once branches have split, they can no longer interfere with each other in any practically accessible way. The branching is not time-symmetric from the inside. It is something that happens in one direction, creating more branches, never fewer. And this directional quality of branching, the fact that the tree of universes grows rather than shrinks, is itself a form of the arrow of time, the same thermodynamic asymmetry that we discussed earlier, now appearing at the level of the quantum multiverse rather than the ordinary universe. The arrow of time has not been eliminated, it has been displaced. It now lives in the branching structure of the multiverse rather than in the individual universe. And time in the many worlds picture is not eliminated, but it is deeply strange. You are in one branch, one thin slice of an unimaginably vast quantum tree, with no privileged claim to being the real version, moving forward in a direction that the fundamental physics doesn't require you to move in a universe that is, at the level of the whole wave function, completely symmetric and timeless, while at the level of your branch, irreversibly branching forward, creating a past you remember and a future you anticipate, both of which are, in the widest sense, already there in the wave function, just in different branches. And now here is a question that may be the most disorienting one yet. If the block universe is correct, or if the many worlds interpretation is correct, or if Barber's timeless physics is correct, or if any of the A narrative of past and future, complex enough to experience the present moment as special and vivid and undeniably real, you are in a deep sense a model-building system, a system whose most important function is generating an accurate enough representation of reality to navigate it effectively. And the most fundamental element of that model, the element that structures everything else, the element without which the model would not function, is time. Your model of reality is built on time the way a building is built on a foundation. Every other feature of your experience, your sense of self, your memories, your plans, your emotions, your relationships, your sense of meaning and purpose, all of it rests on the foundation of temporal experience. And what physics is telling you, from multiple independent directions with increasing precision and increasing confidence, is that the foundation may not be there, that the building is standing on something that, at the deepest level, does not exist in the way the building assumes it does. There is a metaphor that might help to make this vivid, though like all metaphors, it will eventually break down at the edges. Imagine a vast, perfectly still ocean. The ocean has no surface features. It is smooth, undifferentiated, extending in all directions without any markers of here or there, now or then. It simply is. Now imagine that in certain regions of this ocean, specific conditions arise, perhaps temperature gradients or chemical concentrations or some other physical property that cause the water to develop wave patterns. These waves have properties. They have peaks and troughs. They move in a direction. They have a frequency and a wavelength. They interact with other waves in complex ways. From the perspective of someone embedded in the wave, someone who exists only within the wave and has no access to the underlying still ocean, the wave is everything. It is the whole world. It has a direction. It has a past, where the wave came from, and a future, where the wave is going. The wave feels like a real, substantial thing moving through a medium, but the wave is not a substance. The wave is a pattern. The underlying ocean does not move when a wave passes through it. The water molecules merely oscillate up and down. The wave is an emergent phenomenon, a pattern of organized oscillation in a medium that is itself still and undirected. And when the conditions that sustained the wave dissipate, the wave dissolves back into the still ocean without leaving a trace. It never was a thing, in the sense of a persistent, bounded substance. It was always only a pattern. You, and your experience of time, may be something like the wave. The experience of time flowing, of being embedded in a sequence of moving from past to future, may be a pattern that arises in the right conditions, in complex systems with the right kind of thermodynamic structure, and dissolves when those conditions are no longer met. The underlying reality, the ocean, may be still, timeless, undirected, and your sense of being in time may be the view from inside the wave, looking out at a motion that is real as a pattern, but is not inscribed in the medium that sustains it. The question of what happens at death takes on a very specific and strange quality in the context of these ideas. Most human cultures and most human intuitions model death as the end of a journey through time, the moment when a person who has been moving through time stops moving. The self that existed through time ceases to exist. The stream of consciousness which has been flowing through the sequence of moments runs dry. But if there is no stream, if the block universe is correct and all of your temporal stages coexist simultaneously in the four-dimensional structure of space-time, then death is not the end of a journey in the way you ordinarily think of it. It is simply the last slice of the block that your world line occupies. Every moment of your life, every experience you have ever had and ever will have, is there in the block, frozen and complete, none more present than any other, none more real than any other. The moment of your death is no more final than the moment of your first birthday, in the sense that both are simply there at their respective coordinates, equally real, equally permanent. Your life, in the block universe, is not a story that ends. It is a four-dimensional shape that simply is from one end to the other, all at once. And that shape includes every moment of joy and pain and confusion and clarity, and all the ordinary, unremarkable moments between them, all of it existing with the same quiet, timeless permanence as a mathematical theorem. This does not make death less significant from within your experience. From inside the world line, from the perspective of the consciousness moving through the slices of the block, the last slice is still the last. There is still a final moment of awareness, after which there is, for that consciousness, nothing. The block universe does not promise subjective immortality. It promises only that the events of your life are real and permanent in the sense that they occupy their positions in the four-dimensional structure of space-time and will always have done so. Nothing can unmake them. The moments you have experienced cannot be taken away, not because they persist in some afterlife, but because they are fixed in the geometry of space-time with the same permanence as any other physical fact. In a strange and perhaps surprisingly comforting way, the block universe is a universe in which nothing is truly lost, because nothing ever truly passes away. The past does not disappear. It is there, exactly where it always was, at its coordinates in the block. This is not the same as saying the past matters in the sense of being accessible or causally relevant, but it means something. It means that the moments you have lived are not shadows that dissolve as they recede. They are facts, permanent, indelible, real. But we need to be honest about the limits of comfort here, because the block universe, taken fully seriously, also eliminates something that most people consider central to a meaningful life: genuine novelty. In a block universe, nothing is truly new. Everything that will happen has, in a certain sense, already happened. The future is already there. The choices you have not yet made are already made, encoded in the block at their respective coordinates. The discoveries you have not yet made, the conversations you have not yet had, the experiences you have not yet had, all of them exist at their positions in the block, waiting only for your experience to reach them, not for them to come into being. There is no genuine becoming. There is only the traversal of a structure that is already complete. And if you find yourself reaching for the word "but," if you feel the need to object that this cannot be right because you feel genuinely open to different futures, genuinely undetermined in your choices, genuinely capable of novelty, you are exactly right to feel that. That feeling is real. It is one of the most vivid and fundamental features of your experience. But the block universe suggests that the feeling is perspectival rather than metaphysically accurate, a feature of not yet knowing what the block contains ahead of you, rather than a feature of the block being genuinely open. The openness is epistemic, a matter of your knowledge, not ontological, a matter of the structure of reality. And the gap between those two things, between the feeling of openness and the physics of closure, is one of the places where the human experience of time most dramatically diverges from what the physics says about it. Let us take a step back from the block universe specifically and look at the broader landscape of what physics is telling us, because there is something important to note about the convergence of these different approaches: relativity, quantum mechanics, thermodynamics, loop quantum gravity, string theory and its holographic implications, the amplituhedron, the Wheeler-DeWitt equation, Barber's timeless physics, Rovelli's relational approach. These are not all saying exactly the same thing about time. They disagree on specifics. They disagree on interpretation. Some are in tension with each other, but they all share something. They all find time to be problematic at the fundamental level. They all find that time, when you follow it down to the deepest level accessible to the theory, either disappears, becomes relational rather than absolute, loses its direction, or emerges from something more fundamental that does not have it. The convergence is not perfect, but it is striking. From every direction that physics approaches the fundamental structure of reality, the concept of time becomes more elusive, more suspect, more clearly something that requires explanation rather than something that does the explaining. In the history of science, when something that seemed fundamental turns out to require explanation, when something that seemed like a bedrock becomes a phenomenon that needs to be derived, this is usually a sign of genuine scientific progress. Temperature was once thought to be a fundamental property of matter. Then statistical mechanics revealed it to be an emergent property, a description of the average kinetic energy of large numbers of molecules. Temperature did not cease to be real, but our understanding of what it was changed. It went from being a bedrock to being a phenomenon. Sound was once thought to be a fundamental medium, the ether of hearing. Then the wave theory of sound revealed it to be a pattern of pressure variations in a medium that is not itself sound. Sound did not cease to be real, but its ontological status changed. It became an emergent pattern rather than a primitive substance. And over again in the history of science, things that seemed like bedrock, that seemed too fundamental to be explained in terms of something else, turned out to be emergent phenomena arising from deeper levels of reality that were very different from the surface appearance. Time may be the most important, the most intimate, and the most disorienting example of this pattern that science has yet encountered. There is a particularly strange corner of physics that deserves attention here, one that most science communication glosses over, but that physicists find genuinely profound. It is the Unruh effect, and it reveals something about the relationship between time, motion, and the very structure of what we call the vacuum of space. The vacuum, in quantum field theory, is not empty. It is the lowest energy state of the quantum fields that permeate space, and it is filled with quantum fluctuations, virtual particle pairs constantly appearing and disappearing, a roiling foam of quantum activity. Now, according to the Unruh effect, predicted in 1976 by the physicist William Unruh and closely related to Hawking radiation from black holes, an observer who is accelerating through space will detect this vacuum as a warm thermal bath of particles, while an observer who is not accelerating will detect the same quantum vacuum as being empty. Two observers in the same region of space, one accelerating and one not, will disagree not just about the temperature of the vacuum, but about whether there are particles there at all. The accelerating observer detects real, warm, thermally distributed particles. The non-accelerating observer detects nothing. And crucially, this disagreement is about something that is supposed to be physically real, the particle content of a region of space. The Unruh effect reveals that even the concept of a particle, one of the most basic ontological units of physics, is not absolute. It is observer-dependent. What one observer calls a particle, another observer, moving differently, does not see as a particle at all. And this observer dependence is tied directly to time. It arises because different observers moving along different trajectories through space-time have different notions of positive frequency, which is to say different notions of what counts as a particle vibrating in the usual direction in time. The distinction between particles and antiparticles, between positive and negative frequency modes, depends on a choice of time direction. Change the trajectory, change the relationship to time, and the particle content of the vacuum changes. This is a deeply unsettling result because it suggests that even the most basic ingredients of the physical world, the particles that make up matter, are not fixed, objective entities that all observers agree on. They are features of a description that depends on how the observer is moving through space-time, which is to say, on how the observer is related to time. The particle content of the universe is, in this sense, time-dependent and observer-dependent. Take away the observer's relationship to time, and you have taken away the clarity of what counts as a particle. At this point, you may be experiencing something that is hard to name, but that is real and recognizable if you have been following closely. It is a kind of progressive unmooring. Each new piece of evidence, each new argument, each new direction from which the problem of time reveals itself, loosens another handhold on the solid, reliable, intuitive picture of the world that you started with. You began with time as the most self-evident of all facts, the ground floor of reality, the one thing that needed no justification, and you have watched it progressively problematized, relativized, dissolved, made emergent, made observer-dependent, made perspectival, until the question of what time actually is has become not just unanswered, but perhaps unanswerable in the terms that the question was originally asked. And you are left holding something that is difficult to characterize. Not quite knowledge, not quite ignorance, but something in between. Something like the experience of having had a concept that served you well for your entire life, suddenly turn transparent in your hands, suddenly reveal itself to be more fragile and more constructed than you had ever suspected. The philosopher Henri Bergson, who spent his life thinking about the nature of time and whose work is unfortunately underappreciated in contemporary philosophy of science, made a distinction that is relevant here. He distinguished between what he called lived time or duration, the time of experience, the continuous flowing qualitative stream of consciousness, and mathematical time, the spatialized, measured, quantified time of physics, the time that appears in equations as a coordinate, as a dimension, as a parameter. Bergson argued that physics necessarily spatializes time, turning it into something that can be measured and mapped and mathematically manipulated, and that in doing so, it loses precisely the thing that makes time what it is in experience: its flow, its directedness, its qualitative texture, the way it feels different from space. Bergson's critique was controversial and was largely dismissed by the scientific mainstream, partly because of a famous encounter with Einstein in 1922, in which the two men fundamentally talked past each other, and partly because Bergson seemed to be arguing against the validity of the special theory of relativity, which was a difficult position to sustain, given the evidence. But there is something in Bergson's core distinction that is more profound than the controversy around it suggests. He was pointing to the gap between the physics of time and the experience of time, the gap that we have been circling throughout this entire inquiry, and insisting that this gap is real and important, and cannot be simply dismissed by saying that the physics is correct and the experience is an illusion. Because here is the thing: if the experience of time is an illusion, it is a very strange kind of illusion. Ordinarily, an illusion is a false perception of something that exists differently from how it appears. You see a straight stick that appears bent in water. The stick is real. The water is real. The bending is an optical effect of refraction. There is a fact of the matter about how the stick is, and the illusion is a failure to perceive that fact accurately. But with time, if the physics is correct that time at the fundamental level is not what we experience it as being, the situation is more complex, because the experience of time is not a false perception of something that exists differently. It is an experience that may not have any direct physical correlate at all. The experience of time flowing, of the present moment being special, of the future being open, these experiences may not be perceptions of external facts at all. They may be something generated entirely internally by the dynamics of a complex conscious system, without any corresponding external reality. They would then be less like the bent stick illusion and more like the experience of being in a dream. In a dream, you can perceive time passing, you can feel that events are happening in sequence, you can have the experience of before and after, without there being any external temporal facts that your experience is tracking. The time of a dream is generated entirely by the dreaming mind. It is real as experience. It corresponds to nothing external. If your waking experience of time is more like the time of a dream than the time of a physical measurement, then you are in genuinely strange territory. Not because your experience is worthless or unreliable for practical purposes. It clearly is reliable enough for you to function and to build an extraordinarily complex civilization, but because the story you tell about the relationship between your experience and the external world is wrong in a deep way. You think your experience of time is tracking something real and external. You think the present moment you feel is a real feature of the universe. You think the flow of time you experience is a genuine physical process happening out there. And the physics is saying, with increasing insistence and from an increasing number of directions, that none of that is right. The experience is real. But what it corresponds to, out there in the physical world, is something far more subtle and far less familiar than the naive picture suggests. Let us talk about something that rarely comes up in discussions of time, but that seems relevant here: the relationship between time and information. Information, in the technical sense used in physics and computer science, is a measure of the number of possible states a system can be in. Shannon's information theory, developed in the 1940s, defined information in terms of the reduction of uncertainty, the number of yes or no questions whose answers are determined by the state of a system. What is increasingly apparent in modern physics is that information is not just a convenient description of physical systems. It may be what physical systems fundamentally are. The physicist John Wheeler, whom we met earlier, spent his later years developing the idea that he called it from bit, the notion that every physical entity, every it in the universe, derives its existence from information, from binary choices, from questions that the universe in some sense poses and answers. In this view, physical reality is, at its deepest level, informational. The universe is not made of matter and energy in the traditional sense. It is made of information, and matter and energy are what information looks like from certain perspectives. And here is where this connects to time. If the universe is fundamentally informational, then time, as we experience it, is intimately connected to the processing of information. The arrow of time, the direction from past to future, corresponds to the direction from ordered to disordered information, from low entropy to high entropy, from a state that carries more information about the detailed microstate of the system to a state that carries less. The past is the direction in which information about the current state of the universe is concentrated and available. The future is the direction in which information about the current state of the universe is dispersed and becomes unavailable. And this is not just a metaphor. Physicists like Charles Bennett and Rolf Landauer have shown that there are deep connections between information theory and thermodynamics, that erasing information requires energy and generates heat, that computation has a thermodynamic cost, that the relationship between information and entropy is not merely analogical, but is a genuine physical identity. The arrow of time is the direction in which information is processed, dispersed, and lost. And if information is what the universe is fundamentally made of, then the arrow of time is not just a feature of the universe's evolution, it is a feature of the universe's computational structure, of the way in which the information that constitutes the universe is organized and processed. This framing, the informational framing of time, has some interesting implications for the question of whether time is real. If time is the direction of information processing, and if information processing is what happens when physical systems interact in ways that transfer or transform information, then time may be real in exactly the same sense and to exactly the same degree that information processing is real, which is to say, real as a phenomenon, real as an organizational property of physical systems, real as something that makes a difference to how systems evolve, but not necessarily real as a primitive, fundamental, observer-independent backdrop. Information is always information from some perspective, relative to some system that has the capacity to be in different states. And time, as the direction of information flow, may be similarly perspectival, similarly dependent on the existence of systems that can process information, and similarly absent from the deepest, most fundamental level of physical description, where there are no systems and no perspectives, only the timeless mathematical structure of the whole. We keep returning to this tension between the inside view and the outside view, and it is worth naming it explicitly, because it is not going away. From the inside, time is real. It is the most real thing. It structures everything. It is the medium of experience, the ground of consciousness, the skeleton of selfhood. From the outside, from the perspective of physics looking at the universe as a whole, time keeps disappearing, keeps becoming secondary, keeps turning out to be something that needs to be explained rather than something that does the explaining. These two views, the inside and the outside, are both legitimate. They are both genuine perspectives on something real, but they are dramatically inconsistent with each other, and there is no agreed-upon framework that reconciles them. There is no theory that explains why the inside view feels the way it does given what the outside view reveals. There is no bridge between the phenomenology of time and the physics of timelessness that everyone agrees on, and this is not a detail. This is one of the deepest open problems in the entire intellectual enterprise. It sits at the intersection of physics, philosophy, neuroscience, and mathematics, and none of those disciplines has given it a fully satisfying answer. The philosopher of time, Craig Callender, has spent years mapping this territory, and one of his most useful contributions is the observation that much of the confusion about time comes from conflating several different things that we call by the same name. There is the time of physics, the coordinate that appears in equations. There is the time of thermodynamics, the direction defined by entropy increase. There is the time of experience, the flowing, directed, present tense quality of consciousness. There is the time of memory and anticipation, the psychological extension into past and future. There is the time of causality, the asymmetry between causes and effects. And there is the time of cosmology, the age of the universe and the evolution of the whole. These are all related, but they are not the same thing. Conflating them leads to pseudo-problems and false solutions. The question, is time real, may not have a single answer, because time is not a single thing. Different aspects of what we call time may have very different statuses. The thermodynamic arrow of time is real, in the sense that entropy really does increase in the universe we observe. The time of physics is real as a coordinate, in the same sense that the x-axis is real as a coordinate. The time of experience is real as a phenomenal quality, in the sense that you genuinely experience it, but whether any of these corresponds to a fundamental mind-independent, ontologically primitive feature of the universe, that is exactly the question that remains open, and the question that physics is increasingly, pressingly, urgently asking. And the urgency is not accidental. We are living in a period of physics that is genuinely unprecedented in its confrontation with the nature of time. The unification of quantum mechanics and general relativity, the great unfinished project of theoretical physics, the problem that has resisted solution for nearly a century, is precisely the problem where the issue of time is most acute. General relativity, Einstein's theory of gravity, treats time as a geometric feature of space-time, a curved dimension that interacts with matter and energy. Quantum mechanics treats time as a background parameter, a fixed external variable against which quantum states evolve. These two treatments of time are incompatible. You cannot simply combine the quantum description of matter with the relativistic description of gravity without running into a fundamental conflict about what time is. And the conflict is not technical in the sense of being solvable by a sufficiently clever piece of mathematics. It is conceptual. It is about what time actually is at the level of the theory. Until we have a quantum theory of gravity that resolves this conflict, we will not know what time is. And the various attempts to find such a theory, loop quantum gravity, string theory, causal set theory, causal dynamical triangulations, and many others, all of them run into the problem of time in their own ways, and all of them suggest, in their different ways, that the resolution will involve time becoming less fundamental rather than more, will involve time emerging from something deeper, rather than being the something deeper from which everything else emerges. Causal set theory is worth mentioning here, because it offers a particularly striking and concrete picture of how time might emerge from something more basic. In causal set theory, developed by Raphael Sorkin and others, the fundamental structure of space-time is not a smooth, continuous manifold as Einstein assumed, but a discrete set of events, related only by partial order, by the relation of which events can causally influence which other events. There is no geometry. There is no smooth space. There is no continuous time. There is only a set of discrete events and a causal order among them. Event A can influence event B, or it cannot. That is all. Everything else, all the geometry of space-time, all the smoothness of space, all the flow of time, must be recovered from the causal order of this discrete set. And remarkably, As mathematicians have shown, a randomly generated causal set with the right density does generate something that looks very much like smooth, four-dimensional spacetime at large scales. The geometry is not put in, it emerges. Space and time emerge from the partial order of causal relations, which is itself a much more primitive structure, requiring no metric, no coordinates, no geometry, no background time. In causal set theory, time as we know it is not the foundation. It is built up from something much simpler, the bare fact that some events can influence others and some cannot. And here there is something almost vertiginous in its elegance. The most primitive ingredient of causal set theory is causality, the bare asymmetric relation of influence, the fact that some things can affect other things in a directed way. Time in this picture does not give rise to causality. Causality gives rise to time. Causality, the directed relation of influence, is more fundamental than the temporal structure we call time. Time is what causality looks like when you have a lot of it, organized into a dense network of influencing events, generating an emergent geometry that, at large scales, looks like the flowing, directed, smooth temporal dimension of your experience. Causality is bedrock. Time is the building constructed on that bedrock. And the building, as we have seen, can have very different properties from the rock on which it stands. By now, you have traveled a very long way from where you started. You started with time as the most self-evident of facts, the unquestioned ground of experience, the thing that needed no justification. And you have arrived at a place where time is a construction that may be assembled by your brain from sensory information, by the universe from thermodynamic gradients, by causality from the bare directed relation of influence, by complexity from the interactions of simple, timeless components. You have arrived at a place where the present moment is not a universal fact, but a local, perspectival, brain-generated artifact, where the past is not a receding reality, but a pattern of records and traces that gives the appearance of a history, where the future is not an open territory to be explored, but either a fixed region of the block already fully real, or a pattern of increasing entropy that statistical mechanics makes highly predictable, even though it is not determined at the quantum level, where the flow of time is not a physical process but an experience generated by a system complex enough to store information about the past and model the future, running a simulation of temporal passage that is internally consistent and externally useful, but may not correspond to anything in the fundamental structure of the universe. What is particularly striking about this picture, what gives it a quality of genuine existential weight beyond the merely intellectual, is the completeness with which it undermines the things that feel most certain. Uncertainty about the specific details of quantum gravity is one thing. Uncertainty about the correct interpretation of quantum mechanics is one thing. These are technical uncertainties about specific theories, and they don't necessarily touch the ordinary experienced world. But what we have been building toward is something different. It is the suggestion that the most fundamental, the most intimate, the most undeniable aspect of your experience, the sense of being here, now, in this moment, moving through time, is itself the thing that physics is calling into question. It is not a peripheral uncertainty. It is not a detail. It is the center. It is the ground of everything else. And if the ground is not what you thought it was, then you are floating in a way that is very hard to get comfortable with. There is a question that physicists sometimes ask each other, half seriously and half in earnest, that captures the depth of the problem. The question is, what would it mean for time not to be real? What would the world look like if time were genuinely absent from the fundamental level? And the answer that physicists generally arrive at is, it would look exactly like this. It would look like a universe in which complex systems embedded within it experience a sense of temporal flow, while the fundamental description of the universe contains no preferred time direction, no flowing time, no global present. It would look like a universe in which the arrow of time emerges from thermodynamic gradients rather than being inscribed in the fundamental laws. It would look like a universe in which the equations of quantum gravity are static and timeless. It would look like a universe in which different observers moving at different speeds genuinely disagree about what is happening simultaneously. It would look, in every detail, exactly like the universe we observe. The absence of fundamental time is not a deviation from what we observe. It is consistent with everything we observe. The universe looks exactly the way you would expect it to look if time were an emergent phenomenon rather than a fundamental one. And this is not a trivial observation. Usually when you remove a fundamental ingredient from a theory, the predictions change. But when you remove time from the fundamental description of the universe and let it emerge at higher levels, The predictions do not change. The observations are the same. The physics works the same. The only thing that changes is the interpretation, the story you tell about what is ultimately real and what is derived. This is deeply relevant to how we should assess the claim that time is not fundamental. In science, when a simpler theory explains the same observations as a more complex one, the principle of parsimony, Occam's razor, generally favors the simpler theory. A timeless fundamental physics that recovers the appearance of time through emergence is simpler in a specific sense. It has fewer primitive ingredients. It doesn't require you to assume that time is somehow built into the furniture of the universe before physics even begins. It derives the appearance of time from ingredients that are more basic and that need to be there for other reasons. This does not prove that time is not fundamental. Parsimony is a guide, not a proof, but it means that the burden of proof, in a sense, shifts. If you want to insist that time is fundamental, you need to explain why the fundamental equations don't show it, why the arrow of time requires a separate thermodynamic explanation, why quantum gravity seems to eliminate it, why the block universe follows inevitably from relativity, why the Wheeler-DeWitt equation is static. The timeless view has these things on its side. The view that time is fundamental has, primarily, the immediacy and certainty of your experience on its side. And while that is not nothing, it is also not sufficient in the face of overwhelming physical evidence pointing the other way. There is a final direction that we need to explore before we arrive at the end of this inquiry, and it is perhaps the most speculative but also the most philosophically urgent. It is the question of what the nature of time tells us about the limits of human understanding. Because what we have encountered throughout this exploration is not just a series of surprising scientific results about a specific physical quantity. We have encountered a recurring pattern, the discovery that the concepts that feel most fundamental, most directly given, most obviously real, are precisely the ones that turn out, on close examination, to be the most constructed, the most derived, the most dependent on a specific perspective and a specific scale of observation. Solid objects turn out to be mostly empty space. Colors turn out to be a mental representation of wavelength. The distinction between past, present, and future turns out to be perspective dependent. The flow of time turns out to be an emergent thermodynamic phenomenon. The present moment turns out to be a neural construction, and each of these discoveries has been greeted initially with resistance, with the deep intuitive feeling that this cannot be right, that this violates something obviously and necessarily true. And each time, the resistance has gradually given way to a new understanding that is stranger and richer, and more accurate than the familiar picture it replaced. But there is something different about time. There is something about the challenge to time that is more destabilizing than the challenge to solid objects or to the reality of color. Because time is not just one feature of your experience among others. Time is the structure of experience itself. Removing it from the fundamental picture doesn't just change what you think the world is made of. It changes what you think experience is. It changes what you think you are. If time is not fundamental, if it is emergent, perspectival, constructed, then the very framework in which you think, the temporal logic of before and after, cause and effect, memory and anticipation, may be a framework that was built for navigating a certain scale of the universe, and that breaks down when you try to apply it to the universe's deepest level. And if that framework breaks down, then the question of what the universe is really like at the deepest level becomes a question that may not be answerable in any language you have available. Not because the answer doesn't exist, but because the answer requires a kind of thinking, a kind of understanding that is not temporal in structure, and all of the thinking you are capable of is temporal in structure. Every sentence you construct has a before and an after. Every argument you make moves from premises to conclusions. Every experience you have is ordered in time. You cannot step outside of time to look at the timeless reality, because you are a temporal being. Your consciousness is temporal. Your tools of understanding are temporal. And if the universe at its deepest level is timeless, then you are trying to understand something that is, in a fundamental sense, beyond the reach of the kind of mind you have. This is not a counsel of despair. It is not a reason to stop trying. The history of science is full of cases where human understanding managed to partially grasp things that lay beyond the range of direct intuition. No one has an intuitive feel for quantum superposition. No one has an intuitive feel for the curvature of four-dimensional spacetime, and yet physicists have developed mathematical frameworks that accurately describe these things, that make correct predictions about them, that allow us to build technologies that exploit them. Mathematical understanding is different from intuitive understanding, and it can reach further. But there is always a question of what mathematical understanding amounts to, whether it constitutes genuine comprehension of the thing itself, or whether it is a sophisticated way of navigating a map without ever experiencing the territory. And with time, this question is particularly acute, because the map of time that physics is drawing, the timeless or near-timeless fundamental structure, is so radically different from the territory of time that you inhabit, the flowing, directed, present tense territory of your experience, that the gap between map and territory seems impossible to close. Not just practically difficult to close, impossible in principle, given what you are. And yet here you are, here we are, in this moment, in what feels with absolute and undeniable certainty like the present, carrying a past that feels real and lost and irretrievable, looking toward a future that feels open and uncertain and genuinely not yet determined, feeling the seconds tick past with that specific, intimate, impossible-to-ignore quality that makes time so real and so present in every moment of your waking life. And the question that sits beneath all of this, the question that this entire inquiry has been circling around from the beginning, cannot be dismissed or answered or resolved. It simply has to be held. The universe may not have time, and yet you do. Something generates it. Something creates the experience of being in it. Something makes the present moment feel like a real location rather than a statistical artifact. Something makes the future feel open rather than fixed. Something makes memory feel like contact with a real past rather than the mere presence of records. And that something, whatever it is you, or is something that you are part of, or is something that uses you as its instrument. And the nature of that something, the mechanism by which a timeless universe gives rise to beings who experience time as the most undeniable fact of existence, is one of the deepest and most completely unanswered questions that human intelligence has ever encountered. Think about what you were doing before you started reading this. You were moving through your day, making choices, feeling the pressure of things that needed to be done, remembering things from earlier, anticipating things that were coming. You were, in other words, living inside time the way you always do, the way you have always done, the way every human being who has ever existed has done, without question, without doubt, without the slightest hesitation about whether the ground beneath that experience was solid. And now something has shifted, not dramatically perhaps, not in a way that will change what you do tomorrow morning, or how you feel when you remember something painful, or how you anticipate something you are looking forward to. The practical machinery of your life will continue to run on time, because it has no other option. You are built for time the way a fish is built for water. You cannot simply step out of it because you have learned that it may not be what you thought, but something has shifted nonetheless. There is a small persistent crack in something that was previously seamless. The clock on the wall still ticks. The calendar still advances. Your memories still feel like contact with a real past, and your plans still feel like genuine preparation for a real future. All of that continues, but underneath it, beneath the familiar and reliable surface of temporal experience, there is now a question that did not used to be there, or that was there but dormant, and that has now been activated. The question is not one that can be answered by thinking harder or reading more or waiting for physics to catch up. It is a question that may be permanently, constitutively open, because the tools we would need to answer it are precisely the tools that the question puts in doubt. You cannot use time to determine whether time is real, any more than you can use a ruler to measure the ruler itself. The physicists are still working. The mathematicians are still building frameworks. The philosophers are still clarifying the questions and mapping the conceptual territory. The neuroscientists are still probing the neural architecture of temporal experience, finding new ways in which the brain's construction of time is more elaborate and more surprising than anyone had previously suspected. The cosmologists are still looking back toward the earliest moments of the universe, trying to understand what it means to say that time began, trying to imagine what lies on the other side of that beginning, trying to determine whether the concept of before even applies to a moment that may itself be the origin of the concept. All of this work is ongoing. All of it is real and rigorous and important, and all of it, from every direction it approaches the problem, keeps arriving at the same uncomfortable frontier, the place where time, followed far enough and examined closely enough, stops being something you can take for granted and becomes something you can no longer quite believe in, and yet cannot quite stop experiencing. The universe is approximately 13.8 billion years old, if the concept of age applies to it at all. If the time we use to measure its age is something the universe itself possesses, rather than something we are projecting onto it from our position inside it, in those 13.8 billion years, or in that single timeless mathematical structure that merely appears to be 13.8 billion years old, from a certain internal perspective, something has happened that is in its own way as remarkable as any discovery physics has made. Somewhere on a small rocky planet orbiting an ordinary star in the outer spiral arm of an average galaxy, matter has organized itself into a form complex enough to ask the question of whether time is real. The question comes from inside the universe, from a system that is made of the universe, and it is a question about the universe's most fundamental structure. The universe is, through you, questioning whether one of the most basic features of your experience of it is a genuine feature of it at all. And the answer that comes back, from the equations and the experiments and the careful, rigorous, decades-long work of people who have dedicated their lives to this question, is something that no clean resolution can contain, because the honest answer is not yes and it is not no. The honest answer is that time is real at the level where you live. It is real in the sense that the physics of your scale, the scale of human bodies and human time spans and human scale velocities and gravitational fields, is accurately described by theories that include time as a central ingredient. It is real in the sense that your experience of it is a genuine experience, not a hallucination, not a mistake, not a confusion. It is real in the sense that the choices you make genuinely influence what happens to you, and in the sense that the past is genuinely different from the future in ways that matter enormously for how you live. All of that is real. None of that is being taken away, but it is not fundamental. It does not go all the way down. It is not written into the deepest grammar of the universe. It emerges. It crystallizes. It appears when complexity reaches a certain level, when thermodynamic gradients create a difference between past and future, when conscious systems arise that can store memories and build models of the future, when the universe becomes, in certain local pockets of organized complexity, something that can experience itself as being in time. Time is what the universe looks like from the inside, from the perspective of a certain kind of complex, memory-possessing, future-anticipating system. And what it looks like from the outside, from the perspective of the physics of the whole, may be something for which we do not yet have a word, and may never have one, because every word we have is already infected with time, so you are left here, in this moment, in this specific, unrepeatable, vividly present instant of awareness. The room around you is real. The sensations in your body are real. The thoughts moving through your mind are real. And somewhere beneath all of it, beneath the solid, reliable, moment-to-moment texture of your experience, the universe is doing something that your experience cannot fully represent. Something timeless is generating the experience of time. Something static or something relational or something informational or something that we do not yet have the mathematics to describe is giving rise to the river you are swimming in, to the flow you feel, to the present moment that feels like the only moment that has ever mattered. And you cannot get outside of it to see what that something is. You can only feel the current and know now that the current is not the whole story, that the river you are swimming in may not be a river at all, that what feels like movement may be stillness, seen from the inside, that what feels like the present may be everything, everywhere, all at once, experienced from one particular angle, through one particular set of eyes, in what feels, with absolute and undeniable certainty like right now. And the deepest thing about all of this, the thing that stays with you after the physics and the philosophy and the neuroscience have been set aside, is not a fact or a theory or a conclusion. It is a feeling. The feeling of standing at the edge of something that your mind can gesture toward but cannot cross. The feeling of having followed a question as far as it can be followed with the tools you have, and arriving not at an answer, but at a deeper silence. The clock is still ticking. The seconds are still passing. The present moment is still here, vivid and immediate and undeniable. And somewhere in the heart of that undeniable present, the question is still alive, still open, still asking itself in the only language it has. If time is not real, then what is this?